Moonshot AI has introduced a model with 2.8 trillion parameters, almost 3 times the size of Kimi K2. It supports a 1 million token context window. It can understand images and video, work on coding projects for hours, and its full weights are expected to be released publicly. But the strangest number behind Kimi K3 is not 2.8 trillion. It is this. The model contains 896 experts, but for each token, it activates only 16 of them. So when you type a word into Kimi K3, the entire 2.8 trillion parameter model does not suddenly switch on. Instead, a router examines that token and decides which small group of experts should process it. On paper, this sounds like the best of both worlds, the knowledge capacity of an enormous model without paying the full compute cost of a dense model of the same size. But once Kimi K3 is deployed on real hardware, the story becomes much more complicated. Moonshot itself recommends a supernode containing at least 64 accelerators for efficient deployment. So the real question is not simply, how large is Kimi K3? The real question is, how did Moonshot make the model this large without allowing attention and compute costs to completely explode? And if only 16 experts are active for each token, why does the model still need something that looks like a small data center? To answer that, we need to follow a single token through 3 different dimensions: through the length of the context, through the depth of the network, and finally, across hundreds of experts. Let's begin with Kimi K2. K2 was a 1 trillion parameter mixture of experts model. It contained 384 experts, selected 8 of them for each token, and activated roughly 32 billion parameters. Its official context window was 128,000 tokens. With K3, total capacity increases to 2.8 trillion parameters. The number of experts grows from 386 to 896. The model selects 16 experts instead of 8, and the context window jumps from 128,000 to 1 million tokens. But one important number has not been published yet: the exact number of active parameters in Kimi K3. We cannot simply divide 16 by 896 and claim that only 1.8% of the model is active. Some parameters belong to attention layers, embeddings, routers, and possibly shared experts. Until the full technical report is available, any precise active parameter count would be a guess. That distinction matters. The 2.8 trillion figure describes the model's total capacity. It does not tell us the true cost of producing each token. Now let's look at the first major bottleneck. How does a model remember a context containing 1 million tokens? In a conventional transformer, every new token needs to examine earlier tokens to understand the context. That is manageable for a short paragraph, but once the context grows to hundreds of thousands or even 1 million tokens, 2 major costs appear. During the pre-fill stage, the model must process a huge amount of information. Then, during decoding, it needs to preserve and repeatedly access the keys and values from previous tokens inside the KV cache. As the context becomes longer, the model is not only performing more computation, it is also moving much more data between memory and the compute units. On modern GPUs, this movement of data can become a bottleneck before the raw arithmetic capacity of the chip is fully used. This is where Kimi Delta Attention, or KDA, enters the picture. Instead of keeping the entire past open as an ever-growing archive of keys and values, KDA tries to compress previous information into a state that can be updated over time. You can think of it as a working memory that is rewritten whenever a new token arrives. The word delta is important. The model does not simply keep adding information forever. It learns which part of the memory should change, while a gate controls how strongly new information should be written or old information should be forgotten. This compressed state does not completely replace precise attention. Kimi Linear, the architecture that first demonstrated KDA, uses a hybrid design, combining KDA with multi-head latent attention. Kimi K3 also combines KDA with gated MLA, although the full layer arrangement has not yet been described in the upcoming technical report. The potential advantage is clear. The memory cost of long context no longer has to grow in exactly the same way as full attention, and decoding across extremely long inputs can become much faster. In the Kimi linear paper, a smaller experimental model with 48 billion total parameters reduced KV cache usage by as much as 75% and achieved up to 6 times higher decoding throughput at a 1 million token context. But we need to be careful here. Those numbers came from a different model and a particular experimental setup. They should not be copied directly onto Kimi K3. What we can say is that K3 uses the same family of ideas, not that K3 is automatically 6 times faster in every real deployment. So KDA is the first part of the design, compressing information across time. But a model does not only grow along the sequence dimension, it also becomes deeper, with information passing through many layers, and that creates a second bottleneck. In most modern transformers, the output of each layer is added to a residual stream. Imagine a notebook where every layer writes its own note on top of all the notes that came before it. This helps information and gradients travel through deep networks. But there is a hidden problem. Everything is repeatedly added with roughly fixed weight. As the network becomes deeper, useful signals from specific layers can become diluted inside a growing mixture of previous outputs. The magnitude of the hidden state can also grow in an uncontrolled way. Attention Residuals, or ATTNRS, is Moonshot's proposed solution. Instead of blindly adding every previous representation, the current layer uses a small attention mechanism to choose which earlier representations matter and how strongly they should contribute. In other words, the model does not only use attention across tokens, it also learns to use attention across its own depth. If an early layer has recognized the shape of an object, while a later layer has discovered a spatial relationship, a deeper layer does not need to receive an equal mixture of everything. It can retrieve the representation that is most useful for the current computation. Full attention across all previous layers would introduce its own memory and communication cost. That is why the ATTN-RES paper also introduces block ATTN-RES. Instead of selecting from every individual layer, it groups layers into blocks and retrieves block-level representations. That gives us the second part of the architecture, selective retrieval across depth. Our token has now received compressed information about the long context through KDU and selected useful representations from earlier layers through ATTN-RES. Next, it must enter the mixture of experts system. In a dense model, almost every parameter in a feed-forward layer is used for every token. In a mixture of experts model, the feed-forward capacity is divided among many separate expert networks. A router chooses only a small number of them for each token. A token from a piece of source code might be routed through a combination of experts that have become useful for syntax, logic, and tool use. A token from an image or a legal document may take another route. These experts do not necessarily develop clean, human-readable job titles, but a statistical division of labor emerges during training. Kimi K3 uses a system called Stable LatentMoE and activates 16 experts out of 896 for each token. This creates a serious engineering problem. If the router sends too many tokens to a few popular experts, the accelerators holding those experts become overloaded while other accelerators sit idle. The speed of the entire system is no longer determined by its fastest chip. It is determined by its most congested route. Moonshot says it uses a method called Quantile Balancing to handle expert allocation. Instead of relying on manual rules and a sensitive hyperparameter, it derives the allocation from quantiles of the router scores. At this scale, however, computation is only half of the story. A token may need to travel from the accelerator running its attention layer to the accelerator holding its selected expert, and then travel back again. This all-to-all communication can consume the advantage created by sparse computation. That explains why Moonshot discusses fixed-shape expert parallelism, removing host synchronization from the critical path and using a very large high-bandwidth communication domain. It also explains the recommendation for at least 64 accelerators. Mixture of experts reduces the amount of computation performed for each token, but it does not remove the need to store all the model's weights or move tokens between different experts. So what does 2.8 trillion parameters mean in physical hardware? Kimi K3 uses quantization-aware training from the supervised fine-tuning stage onward, targeting MXFP4 weights and MXFP8 activations. To understand the scale, suppose each of the 2.8 trillion weights occupied exactly 4 bits. The raw weights alone would require about 1.4 terabytes of memory. If that were divided perfectly across 64 accelerators, each accelerator would hold roughly 22 gigabytes of raw weights. But that number includes none of the additional memory required for KDA states or KV cache activations, communication buffers, routing, the inference runtime, replication, and the overhead of the MX formats. So this calculation does not tell us the actual GPU requirement. It only shows why a sparse model can use relatively little active computation and still require an enormous deployment. This is the distinction that often disappears when people discuss open models. Open weights do not mean laptop-sized hardware requirements. Moonshot says the complete Kimi K3 weights will be released by July 27th. At the time this script was prepared, July 22, the full weights and final license had not yet been published, so the accurate description today is that K3 is a model with a promised open weight release, not yet a model that anyone can freely download and deploy. Now, let's put the entire journey together. Imagine asking Kimi K3 to find a bug inside a huge software repository. First, project files and a long interaction history enter the context. KDA layers compress parts of that history into manageable states, while gated MLA layers provide more precise access where it is needed. Then, a 10 RES allows each block to retrieve useful representations from the depth of the network, instead of receiving only a uniform sum of everything that came before. Inside the MOE layers, the router selects 16 experts for the current token. Tokens travel across the accelerators holding those experts, get processed, and then return to continue through the network. After forming a hypothesis, the model may call a terminal tool, run a test, inspect a screenshot, and use the result to decide what to do next. So, K3's agentic ability does not come from one benchmark or from 2.8 trillion parameters alone. It comes from the interaction of 4 things: massive capacity, long context memory, sparse expert routing, and post-training designed for long-horizon tool use. And if the agent harness fails to return the complete thinking and tool call history to the model, that entire chain can become unstable. So, what do the benchmarks actually tell us? Moonshot itself acknowledges that K3's overall performance still trails the strongest proprietary models in its comparison, Claude Fable 5 and GPT 5.6 Sol, even though K3 appears competitive or sometimes stronger on particular coding, agentic, and kernel optimization tasks. For example, Moonshot reports a score of 67.3 on Deep SWE version 1.1 using the Mini SWE agent harness. It also reports 90.4 on BrowseComp when K3 uses its full 1 million token context without context management. But the comparison table is not perfectly clean. Some models were run with Kimi code, some with Claude code, and others with Codex. In several evaluations, competitor results came from different harnesses or slightly different hardware and test branches. K3's results were also reported with reasoning efforts set to maximum. These results are strong evidence that K3 is serious about long-horizon coding and tool use. They are not yet enough to declare it the universal winner. The same caution applies to the impressive demonstrations, building a Triton-like compiler, designing a chip in a 48-hour autonomous run, or processing thousands of documents. These are company case studies. They show what may be possible, but not the model's success rate across 100 unseen projects. The official API price is 30 cents per million cached input tokens, $3 per million uncached input tokens, and $15 per million output tokens. That 10 times difference between cached and uncached input is not accidental. In coding workloads, large parts of the repository and instruction prefix stay unchanged across many requests. If the prefix remains stable, the serving system can reuse cached computation instead of repeating the entire prefill stage. Moonshot claims its own API reaches a cache hit rate above 90% in coding workloads. That is an internal workload-dependent claim, but it reveals something important. The economics of K3 depend not only on the model architecture, but also on the caching and serving infrastructure around it. K3 also keeps thinking mode enabled. Reasoning tokens count towards usage, and preserved thinking history continues to occupy context space and can increase the bill. So, a 1 million token context window does not mean that using 1 million tokens is cheap or free. It can be extremely useful for large projects, but poor history and cache management can damage both quality and cost. Moonshot also lists several limitations. First, K3 is sensitive to its thinking history. If an agent harness fails to return the complete previous reasoning state, or if you switch to K3 in the middle of a session, the output may become unstable. Second, the model can be excessively proactive. Because it was trained for difficult long-horizon tasks, it may make unexpected decisions when it encounters minor ambiguity, instead of stopping to ask a question. For an agent with access to files, a terminal, or real systems, that can be both useful and dangerous. Its boundaries need to be defined carefully in the system prompt or an agents.md file. Third, Moonshot explicitly says that K3 still has a noticeable user experience gap compared with the best proprietary models. And finally, several major technical details remain unknown: the active parameter count, exact layer configuration, training data and compute, K3-specific ablation studies, real-world performance across different deployments, and the final license for the weights. Kimi K3 should not be understood only as the largest open model. It is really 3 experiments happening at the same time. KDA asks whether a model can preserve an extremely long history without an enormous conventional KV cache. Attention Residuals asks whether deep layers should blindly accumulate everything that came before or selectively retrieve the representations they need. And Stable LatentMoE asks whether total capacity can reach several trillion parameters, while each token activates only a small fraction of the available experts. Moonshot's early answer looks promising, but the cost has not disappeared. It has moved. The cost moves from full attention into compressed states and caching, from dense computation into routing, and from a single accelerator into the network connecting dozens of them. For users, K3 is already a serious agent for coding and knowledge work. For developers, the 1 million token context and low cached input price could be valuable, as long as the agent harness correctly supports preserved thinking and caching. And for the open model community, the real test begins when the weights, license, runtimes, and complete technical report become available, and we can finally see how well this architecture performs outside Moonshot's own infrastructure. So the conclusion is not that Kimi K3 has defeated every other model. The more important conclusion is this: the frontier model race is no longer only about adding more parameters. It is becoming a race to control how information moves through time, through network depth, and across physical hardware.